We are Wisconsin Robotics, and we are excited to present our 2021 rover, Tempest MkII. Tempest MkII is a further iteration to increase robustness and sustainability, better equipping us for the challenges of the competition.
Our rover uses a 6-view rocker bogie mechanism with a vertical differential bar, which allows it to maintain stability while traversing rough terrain and lifting heavy loads with a robotic arm. It has been completely redesigned to optimize reliability and serviceability. The mechanically simple construction is a compliant structure designed to withstand impacts when driving at full speed without the need of heavy springs and dampers. Each wheel has a Kevlar outer shell with integrated grousers connected via aluminum spokes to a custom wheel hub that is individually driven. A labyrinth seal is integrated into the wheel hub assembly to prevent particle ingestion and allow us to perform outdoor testing even in harsh conditions.
Tempest MkII features a 6 degree of freedom kinematically redundant arm. The arm maximizes range of motion while reducing joint energy consumption. We are implementing inverse kinematics to make holistic arm control easier for our operators by using a mathematical model of the arm in tandem with position feedback from absolute encoders located along the joints of the arm. The worm gear manipulator is smaller and more compact, allowing for more accurate movement. The end effectors have the capacity to interact with the wide variety of objects encountered during the extreme retrieval and equipment servicing missions. The tips of the end effectors were designed to conform to grasped objects, improving grip performance. Additional IP cameras are located to both sides of the arm for visual clarity and to assist with precision manipulation.
The electronic system uses the same embedded system used in last year's rover with a focus on simplicity and repairability. The embedded system uses an NVIDIA Jetson Nano for more processing capability and distribution of logic to perform essential functions. Basic micro roboclaw motor controllers are used to communicate with the motors for operation and integration of encoder feedback. From last year's rover, a breakout board has been implemented to reset certain systems without a full reboot of the entire electronic system, removing the need for an intervention. The rover includes a fisheye camera mounted to a motor for panoramic views, which will be used to both scan the environment during tests and all sides of the rover. For long-distance communication, the rover uses 2.4 GHz and 900 MHz radio systems. Both are proven to have dependable connections throughout the severe conditions of the competition environment.
This year, the software team has taken the opportunity to rebuild the entire software system from the ground up in order to eliminate legacy code and suboptimal design decisions. We devised a 4-layer abstraction over the robot system that guarantees predictability in the organization and behavior of ROS entities. Within this framework, we re-implemented the entirety of robot functionality using ROS Noetic and Python 3, taking advantage of modern language features that allow us to write less buggy and more maintainable code. We've developed a robust serial interface library for driving our motor controllers and other low-level devices in a way that is not only efficient but also safe through the use of watchdogs that automatically halt robot motion in fault conditions. We're now working on implementing real-time arm control using the MoveIt motion planning package, which will allow for more precise manipulation of the environment during the ERDM and equipment servicing tasks. We're also working on integrating our AI solution, which uses data from a LiDAR unit to infer a distribution of nearby obstacles, which we can then use for autonomous navigation towards a goal as determined by our GPS and computer vision systems.
This year, the Planetary Science team has worked on improving the existing design and expanding the testing capabilities of the rover. The soil collection system uses a scoop mounted to a crossbar that is actuated by a lead screw. The new iteration of the scoop is designed to have no gaps when closed to avoid soil spillage. We have expanded our tray to hold more cuvettes for testing, as well as to include mounts for our new funnels that will prevent cross-contamination. The cuvettes contain Buret's and Lugol's reagents, as well as tests for pH and free ammonia. These tests will help us determine if the soil has any signs of extant or extinct life. Lastly, a microscopic imager allows us to gather information about what lies beneath. 300x magnification allows us to examine soil and rocks for signs of fossilization, calcite deposits, and information about conditions in which the rock developed.
The team has emphasized testing and analysis in a socially distanced format to ensure the safety of team members, while also effectively preparing the robot and drive team for the challenges of competition. By integrating a variety of switches and levers into a 5-kilogram design, the team is able to test all necessary functions of the rover's arm using a single unit. Fine manipulation of the end effector is tested and refined using the side panels of the box, while overall arm strength is tested with the entire box itself. Software-related testing of autonomous and teleoperated code has been done remotely through the use of a small-scale rover. Mirroring the hardware components of our competition rover, this testing platform allows us to write and test software in tandem with hardware to access rough terrain and thoroughly test changes made to our drive system. The team operates the rover through a variety of outdoor environments. In addition, the team will critically evaluate and improve upon our readiness for the science task using a series of soil samples and performing performing a number of practice runs. From the design to the team's collection of testing platforms and methods, Tempest MkII is capable of performing successfully in all competition challenges.
Thank you to our sponsors.